Today's Smart Physics lecture will be one that I'm creating, and it's so that we can do more examples of 1D and 2D kinematics as people have been asking. Just some reminders for this week. Homework 2 is due Wednesday, February 11th before midnight. Exam 1 is on Thursday, February 12th, and the day before the exam in class we will be doing a lecture and review for Exam 1, where I'll mostly be lecturing about what will be on Exam 1, and we can do some more example problems if you need to. So let's get started. Example 1. The example reads, a relief airplane is delivering a food package to a group of people stranded on a very small island. The island is too small for the plane to land on, and the only way to deliver the package is by dropping it. The airplane flies horizontally with a constant speed of 432 kilometers per hour at an altitude of 975 meters. The positive x and y directions are defined in the figure. For all parts, assume that the island refers to a point in the distance d from the point at which the package is released, as shown in the figure. Ignore the height of this point above sea level. Assume that the acceleration due to gravity is g equals 9.80 meters per second squared. The question is, if the package is to land right on the island, at what horizontal distance d from the plane to the island should the package be released? Our first step in the goal system is to gather our information. This could also be called givens and unknowns. That's what you need to do in the gathering information part. So we have this nice figure here, and we have some information that's in the problem writing. I'm going to edit up the figure so that we can talk about what each of the givens. So the first thing that they gave us is the velocity of the plane, which is v naught, which is equal, let me get my pen working here, which is equal to 432 kilometers per hour. Okay. The altitude of the plane is 975. That's equal to this h here, 975 meters. This little thing here is indicating which direction is x and y. We want to find d, so d is equal to question mark. And they're also giving us that the acceleration due to gravity is 9.8 meters per second squared. And we should remember that in this coordinate system that will be negative 9.8. The other piece of information that they gave us is that even though they're showing the island as being slightly humped, we're just going to assume that the drop point is at y equals 0. Okay. And so we want to know what this d is. Now, we have to think about, is that the only unknown for this problem? And in actuality, I think we don't have enough information quite to just solve for d using the numbers we have here, which makes this a multi-step problem. So part of gathering information and organizing your approach is to think about what the steps are of the problem, and to decide if it's like a problem that you've seen before. And so you have seen problems like this before on your homework, in particular the problem where if you have a problem where something goes off of a cliff and it's moving with a horizontal velocity. Okay, so let's go to the next part. So I've listed all of these things that we need. I've added one more thing that we need in order to solve this problem, which is the time of the fall. So this is part of the organizing approach, is trying to figure out what else we need. We also need to convert our v naught into meters per second from kilometers per hour. So I'll do that here really quickly. V naught is 432 kilometers per hour. And I will multiply by 60 minutes in 1 hour, multiply by 60 seconds in 1 minute. And I will also multiply by 1,000 meters in 1 kilometer. Okay, so just using unit cancellation, that will get us to meters per second. And the answer is 120 meters per second. Okay, so we have v in the x direction. So this is v naught if we think about it as a vector, it has an x direction, which is 120 in the x hat direction, and it's 0 in the y hat direction. Okay, so that means there's no initial velocity in the y direction. All of the initial velocity is in the x. X and y are uncoupled, so we know that we can get the displacement in meters, which is equal to the velocity times time, and in this case it's the time of the fall. So this is the equation we need to use in the x direction. The problem is that we need the time of the fall, and we need that in the y direction. And so in order to do that, we need to figure out which kinematic equation we should use. Okay, so we want t fall. So we want an equation that has t in it. We have acceleration of the fall, right, is equal to minus 9.8 meters per second squared. We have v initial in the y hat direction, which is equal to 0. Let's see, we don't have v final. We have h, which is, why won't it let me write there? Which is equal to the delta y. So we could use the kinematic equation, which is delta y, or delta x, is equal to v naught y t plus 1/2 a t squared, where both of these t's are the t of the fall. And so using this equation, we can get t fall, and then we can plug it into that equation. So this is going to be our approach. Notice that I haven't plugged in any of our numbers yet. So now that we have this approach, we can solve that initial equation for t fall. So we've got, I'm just going to write it as h is equal to, and we've got v naught y t fall. This is going to go to 0 because v naught y is 0, plus 1/2 a t fall squared. Can solve this for t fall. So we have 2h over a square rooted is equal to t fall. Okay, that t fall is what's going to go into our second equation. So we got d is equal to v naught x t fall. D is equal to 120 meters per second. T fall is equal to the square root of 2h, which is 975, put a little multiply sign there, divided by a, which is 9.8 meters per second. Now let's talk a little bit about signs here. Because we're falling down, this height should actually be negative 975, and this g is also negative, and those minus signs for both of those actually cancel each other out, giving you a positive. If you ever have a square root in your a square root with a negative sign inside of it, please check your units and check your minus signs on your components that go into the square root. It's very likely that there's actually two minus signs that will cancel. You may or may not know that the square root of a negative number can be defined. We use the imaginary number I, but we will not be using that in this class. So that's how I knew that we needed a negative sign on both of these, in addition to the fact that delta y is actually a negative number because it went from 975 to 0. Okay, so using this we can solve, and I need to pull out my calculator. So we get, I'm going to multiply 975 times 2 divided by 9.8 first, and make sure my calculator is in scientific mode. Do the square root. It can either be plus or minus 14, but we know it's not going to be minus because of our coordinate axis, times 120. And so D is 1,600 193 meters. Okay, so that is our answer. And the last thing we need to do is learn from our work. And so we can classify this problem. So there are certain things we can classify. The first thing is that the velocity was only in the x direction. So v sub y initial was equal to 0 to start with. We can also classify problems where the thing falls down. And in that case, we know that delta y is a negative number. And this is a multi-step problem where in order to find the distance in x, we needed the distance in, oh, sorry, not the distance, the time of the fall. And you've probably seen other examples like that.